giving a talk on my progress about this, about my work in as a part of the project. This work is named as Characterization of Steel billets scales generated during the steel milling process. Is in SiderPeru. I'm one of the master students, Luis Borja. Okay. We made a trip in February 2020, and the 13th at SiderPeru to try to see what was the process of production of the iron steel, and to take some samples of each process. So SiderPeru has a process of steel production that consists of 3 principal steps. One is in the arc furnace, the second one is the ladle oven, and finally the casting. In the casting, SiderPeru mainly produce iron steel by using slags of like using steel slugs. They use a lot of steel trash. Using this steel trash to produce all the main production of the steel. So in the arc furnace, they fill the arc by voltaic arc and try to melt in all the steel trash in this case. And during this process, it generates 2 types of samples. It generates, one is the type 1. This is the the red powder that is flowing, that is happen when this fill the arc furnace. The other type of slag that is formed is when they are melting the steel trash. It's like and this is and it seems appears to be like a slag, black slag. We name this type 2. After this melting in the arc furnace, they continue with the second step, that is the process on the part of that is taking part on the ladle oven. So in the process, in this part, they have all the components. Okay. Can you hear me?
Yes, I can hear you well. I can hear you well. Yes. Pratap, raise your volume, Pratap. Okay, go ahead.
Okay. And the second step is there is a process of once it's melting the steel trash, they give the properties of for obtain the final product. In this case, this steel. Steels of for the steel for construction. Yep. In this part they made the reduction samples, so try to reduce the other compounds that in some way affects the final structure of the steel, like phosphor, sulfur, silicium, calcium. This is the reduction of these compounds. and try to elevate the content of iron and oxide and carbon. Once this process of reduction is completed, the final product obtained is the dilution of the next process of this, the reduction in the ladle oven, is the casting process. They takes the content and takes to the contents that has a section, a square section, to the square section, and they obtain the lower bars, that's known as palanquilla. So in the case of the second step, in the second step in the walls, it forms it's the type 1-3 sample, and the other is this remnant material that is in the walls of the ladle oven is used by as a method to extract the iron. So in the case, there is two types of material. This is type 1, which is the remnant in the walls, and the type 2, which is the dismetallized. SiderPeru has a method to obtain the iron, to extract the iron and reduce it. Okay. In the case when in the type 4 sample, it's province of the surface of the elder bars. As you can see, it's indicated by this point. It's like a blank eye. So, and this is produced by the reaction with the surface of the rod, or with the by means it's lowering its temperature, and by the reaction of to the environment. So we'll obtain 25 kilograms of each sample. Okay, this is a photography of our samples. Type 1 and the type 2, that it's come from the oven, the ladle oven, the remnant of the in the walls, and the scales. This light is it forms when it's reacting by the environment. As you can see, this blank this. So to characterize different snakes. Can you hear me? Hello.
Yeah, ahora sí te escuchamos. Continúa.
Okay. Voy a arreglar un momento. Ahora, can you hear me now?
Sí, continúa.
Okay. So the first technique that we used to characterize samples was the SEN EDX and the X-ray. So you can see, this is the spectra. The EDX is spectra for the three samples. for the type 3.1, type 2, in the case of 3.2, three samples. What you can see is that there is a similarity in the content percentage of the chemical elements. In the case of iron and calcium, can I continue?
Ya, voy a quitar mi volumen, ya, para que pueda continuar.
Okay. Can I continue now? Hello. Okay. Profesor, ¿puedo continuar?
Sí, había apagado mi volumen para que continuara, pues no me escuchaba. Ya, continúa, mejor, continúa.
Okay. Sorry for the issue. Okay, so sorry for the issues. Okay, as you can see in the table, there is a comparison of the EDX and the X-ray fluorescence, and there is a similarity in the detection of iron, calcium, and silicate, but there is a difference in the detection of the rest of the minor compounds. This is due to two ways. One is that the sample is not homogeneous, and the other is that the X-ray fluorescence has more penetration depth than the EDX. So this allows this technique to detect more chemical elements than the EDX. Can you the next one, please? This in this case, this is the fluorescence, the X-ray fluorescence spectrum for the sample type 3.1. Okay, so you can strongly pick with high intensity for the iron. And in the table you see the compounds and in percentage the iron that was detected by this technique, and the high concentration in the first row you see the content for the type 3.1. It's the iron, calcium, and silicate as the major complex. Please, the next one. Similarly for the type 3.2, there is a stronger peak with a high density for the iron, for this iron energy. Also, there's major compounds, that's calcium, silicate, and iron. The next one, please. And this is one for the type 4. And the case is iron is in high concentration. There's about 98%. So you can see in the spectrum, there's also a high peak for the iocyanate. The next one, please. Okay. The other technique that we use is the X-ray diffraction to try to detect all the mineralogical phase that are present in our sample. In the case we detect magnetite, hematite, and wustite as the iron oxides, and calcium silicate and calcium manganese silicate. Okay, so the calcium silicate is a compound that is formed by the reaction of calcium oxide and silicate oxide around the okay, this one. The temperature, it has to be 750 degrees. Okay. Please, the next one. In the case of the type 3.2, we also detect hematite, magnetite and wustite, calcium silicate and iron ferrite and calcium iron silicate. So calcium ferrite is formed of 750 Celsius degrees by the reaction of the calcium carbonate and plus hematite. And the other compound is calcium ferrite silicate is from 1460 degrees. It is take place by the reaction of calcium oxide, wustite, and quartz. So this is the phases that we detected, and there is a similar phases detected by the type 2-1, which are the magnetite and wustite. Please, the next one. Okay. The next one is the type 4 sample. So we only detect the iron oxide phases, hematite, magnetite, and wustite. So this is an interesting one sample because this only consists of iron oxide compounds. Please, the next one. The next technique that we use to characterize the samples is the Moss-Wire spectroscopy. So you can see the experimental data is the spectra that is formed by the black dots. And the analyzed result in the spectra is the fitting curve that is in the red color. And the other colors is the subspectra, that is the components. So in the case we can confirm the presence of magnetite. This is the curve, the green curve. The orange and the wine curves are the presence of the case of the magnetite. In the cases depend. This two curves depend of the oxidation state of the ion. So in the cases the ion +2 is the one that has the one that is more smaller, the sextet more smaller than the others, and the color wine. And the orange is that has the oxidation state of the ion +3+. So in the center we observe that there is other two curves that consist only two peaks. This is called doublets. In the case there is no one mineral that I can assign, but there is a suspicion that maybe is related with maybe it can be one could be wustite, as we detect in the X-ray diffraction, and the others may be magnetite, but magnetite in nano-size magnetite. Okay. Please, the next one. The next, please. Hello. Okay. Similarly, the process for type 3-2. We fit in the spectra with 4 sextets and 2 doublets. Also, there's 2 doublets. This is the violet and the cyan color is for the magnetite, also in this oxidation state plus 2 ion 2+ and 3+. And in the table you can observe this. It's parameters that this confirms that there is this can associate with the magnetite. Also, we have the oxidation state 3+. Also confirm the presence of the calcium ferrite in 2 sites, the site A and the site B. The site A is the green color, and the site B is the magenta color. And the other doubles also is the same as I mentioned, but by type C1, that is the suspicious that also there's a Wustite in the doubles in the center of the spectrum. Wustite and maybe a magnetite nanosized. The next, please. Okay, this is the last one. It's the type 4. And this also the sample that only contains all these conformed by iron oxide compounds. Okay, the brown one curve is the associated with the hematite. The magenta and orange is associated with the magnetite, also in the two oxidation states. And similarly, also in the center we have two doubles, one associated, but could be associated with double of magnetite and Wustite. So magnetite in the case of nanomagnetite. Please, the next one. Okay, and the other technique is the magnetometry. So in the left bar we have the hysteresis and the magnetization in the right bar. So in the case we measured at temperatures of 5 kelvins, 300 kelvins, and 400 kelvins. So at first sight we can see that this behavior is like a superparamagnetic behavior, but no short, because there is a lot of contributions of the different compounds. So it's not a sample that is conformed by one compound. It's conformed by different compounds. So this we have to determine what part belongs to each compound that we found by X-ray diffraction and most of our spectroscopy. And also in the insert you can see the standard path that indicates that this sample is a soft material and has a lower remnant magnetization. So the parameters you can see the parameters in the table and below the graphs. And the other in the left bar we have the magnetization at 500 OST and 1000 OST. We can see that there is like a reversibility process for blue curve at 1000 OST, but in 500 OST there is not existence of reversibility. Also, we can see about between 100 and 150, like formation of tiny slopes, changing in the behavior of the curves. Maybe we can associate this with the Bayward transition. This occurs about 114 kelvins. The Bayward transition that is associated with the presence of magnetite in the sample, and we confirm magnetites in the sample by X-ray diffraction and most of our spectroscopy. The next, please. Professor Luis, please, the next slide. Okay, also this the magnetometry for the hysteresis and the magnetization measurements for the sample type 3.2. Similar after the last one is measured at 5 kelvins, 300 and 400 kelvins. Also, we observe that it's a behavior like a superparamagnetic behavior, but it's necessary to make internal research to confirm that what is the exactly behavior of that. Also in the magnetization curve, we can observe that there is a reversibility in the case for 500 Ørsted, but not for the red curve. That is the 100 Ørsted. So in the case also we you see in the row, you see the row, the black row. This indicates that a change in the behavior also, and this temperature and this curve at the temperature of 114. That also it relates to the process to magnetize. So this is due by the Weber transition. Please the next one. The next. Abusolis, please the next slide. Okay, and this is the hysteresis and the magnetization for the sample type 4. As was mentioned before, this sample is only compound. The only compositions that we found in this sample is only iron oxides, so, magnetite, hematite, and wustite. So in the case we measured the hysteresis of 4 different samples, 5 kelvins, 150 kelvins, 300 kelvins, 400 kelvins. In the case we can observe that there is like a slope in the curves. This behavior is very, very similar. Also, as a whole, the hysteresis curves has a behavior of superparent behavior, but we need to confirm this. And also, we observe that this is starting to the saturation magnetization is appearing for all samples about 6,000 Ørsted, and also that there is a reduction in the remanent magnetization and the CONCYTEC field. In the magnetization for this sample, we obtained that there is, as we can observe in the 2 curves, there is no reversibility. In the case of the measurement of 1,000 Ørsted the behavior is very, very close. So the curves are very, very close, but it's not a reversibility process. And the red curve, we see that the Weber transition is more pronounced. There's a more increase, and this happened at 415 kelvins. Another, we can detect another behavior that is about 1454 kelvins. That we can have a suspicion that this may be for the tiny of the particle, for the particle size associated with the particle size. Please, the next one. Please, the next. Profesor Luis, por favor, la siguiente. So, the conclusions that we take is, I made some description of the process of the explanation. So, we found the biochemical elements. There is iron, calcium, and silicate. So for our samples, we detect the 3 oxides. There's magnetite, hematite, and wustite. In the magnetometer measurements, was the case in this hysteresis. It shows a paramagnetic-like behavior, but we need to confirm that. And so most of our spectroscopy also show us the presence of the iron oxides, but in the case to confirm that, as I mentioned before, is that there is the presence of magnetite, but nanomagnetite. We need to take measurements at low temperatures. So in order to do a thorough analysis, please. So that's all my speak, and thank you. And acknowledgements for CONCYTEC, from the seat and the World Bank.
Okay, thank you very much, Luis Borja. Questions? Any questions? Professor Lilian, you have any questions? Your microphone, Professor Lilian.
Yeah, hi, Luis. Hi, Luis Borja. Thank you. Hi. Presentation is good. I was wondering the grain size. How big are the grains of the hematite, wustite, and magnetite? In powder 4, in the type 4.
Luis Borja está preguntando los tamaños de granos de estos de acá, de estos componentes, magnetite, hematite, and wustite.
Okay. No, yet I cannot calculate. I not calculate the grain size. Also, there is an assumption that there is the presence of the magnetite, but I can calculate the size of the sample by doing maybe a triple refinement or using the solver. So now I know.
It would be worthwhile to calculate the grain size by using the William Hall method of the Scher's equation.
Okay, Luis Borja dice que tienes que calcular los tamaños de granos, ¿ok?
Okay, right, yeah, okay. I know it.
Okay, Luis Borja is taking your suggestion and he's going to calculate the grain size later on. Thank you.
Okay, yeah.
Okay. Thank you, Professor.
Have you milled the powder, or this one after the powder came? How big are the particles?
Inicialmente, ¿qué tan grandes son los tamaños de granos? Inicialmente. Explica lo que está en la figura.
Okay.
Okay. So they are quite big, so need to be grounded. Yeah, sure.
In the case is very about very large grains. It is about if a question of diameter is maybe 10 centimeters. For the case of type 1, there's a different size. Yeah, in the case of this case, also it's in different size. No such uniform size. That's in the case. This is raw samples, not
raw samples.
Before the measurements, we have powdered this.
Okay.
Yeah.
But with the oxide, like type 4, with oxide, is there any potential application of the oxide?
¿Hay alguna aplicación de este tipo 4, los óxidos?
The case of the hematite.
De tipo 4, los óxidos. Dice los óxidos.
Yeah, it's the case of the magnetite for the type 4. There's applications. In the case of the aneuploid, we made simulations because there is a suggestion for the professor pattern. Also, I think is using the nanoparticles of hematite in graphene. I don't know if this is your question.
Okay.
Thank you.
Thank you. Okay, thank you. Pratap, any question?
Thank you, Professor Dalia.
Yeah, thank you.
Pratap, any question?
No questions from my side.
Okay. Ya, profesor Ángel Bustamante, un poquito rápido, también podemos terminar. ¿Alguna pregunta, Ángel Bustamante?
No, la lámina 10 showed to me there is un gran error. The blue color is doublet. But in another slide is the magnetized second sextet.
Ah,
I
sí.
confuse. Hay que corregir esa lámina. El color del doblete
Sí,
está
okay.
alterado, entonces eso también no es bueno.
Yeah, I made a confusion assigning the label of the scripts. Entonces, sí, he confundido haciendo asignando los nombres.
No,
sí,
hay dos preguntas. Dos preguntas. El doblete azul es el color de la magnetita, y entonces está errado. Pero también, como lo vi en la vez pasada, no sé de quién, eso de ahí puede ser matemáticamente correcto, el ajuste, pero físicamente no es correcto. Ese Summer Chief corrido hacia allá, ese no está bueno. Yo pienso que el doblete está dentro de la parte rosada. Está ahí. Solamente con la medida al nitrógeno ya puedes saber algo de ese doblete azul. Muy corrido, está hacia el extremo. ¿Ya?
Sí,
Eso hay que hacer urgente, una medida a baja temperatura. Eso no se puede mostrar en los papers del ICAME. Ok, gracias.
Okay, thank you, Professor. Okay.
Okay, correct that. Don't forget to correct that, and also to try to double check also the position. Okay, correct the labels and double check the positions. Okay. Okay. Next question. ¿Alguna otra pregunta del público? From the public? Okay. If there is no more questions, then si no hay más preguntas, entonces ahí también está escribiendo. Si hay más preguntas, entonces ya. ¿Dónde estamos? Aquí estamos.